Then we go to developing a numerical mesh. For the upper respiratory tract. And this upper airway will be reconstructed from medical imaging. So I have uploaded some files on that cloud folder, so make sure that you have access to that. The idea is for me to show how to develop the mesh first on projector, and hopefully you guys can use those files to develop your own meshed geometries. And the geometry will look very similar to this one. A different subject, not this actual person, but it would look very similar. So once we build the mesh, we are going to simulate both breathing and particle transport through that subject's airway. So 1, 2, 3, 4, 5. The sixth topic would be numerical simulation. Of inhaled airflow within anatomically realistic respiratory tract. So I briefly mentioned that when we study this kind of particle transport in the airway, the applications will be twofold. One for drug delivery, one for studying the motion of pathogens. So after we are done with all this, then I'm going to branch into those applications. So the next will be application 1. The respiratory infection onset mechanics. And this is a very interesting subfield that is coming up over the last couple of years. It got triggered, of course, with COVID-19. But as we know, there are many other diseases that can spread through inhaled transmission, through airborne pathways. And what I am doing in my group is develop the fluid mechanics understanding of what is going on inside our airway. There are other groups who are looking at room level spatial transmission. We have some work on that, but that's not what we are going to show here today, and that's not what my focus is right now. I'm trying to understand what is going on inside our body and how the fluid mechanics is impacting that transport. But once I mention this word infection, just knowing fluid mechanics is not sufficient. You need to understand something else as well. So you need to connect the fluid mechanics with things like virology, with things like immunology. And that is really that niche subfield of fluid mechanics plus virology plus immunology plus epidemiology to understand how infections start in our airway. So that is application 1, and I'm going to solve some problems which probably will give you some idea on how you can connect the fluid mechanics data with say, virological parameters. Application 2 is targeted intra-airway drug delivery. So now again, the moment I say drug delivery, just fluid mechanics is not going to be sufficient. Ideally, eventually we need to understand the pharmacological considerations. So from fluid mechanics, you can sort of estimate how much drug particles are going to land at a particular tissue site inside that airway, but whether it is sufficient or whether it is safe, that depends on the pharmacological nature of those particles. And I'm going to touch a little bit on those things as well. So this is application 2. Now after this, we will try and brainstorm on the open questions. The reason being this, the material that I am going to cover today, I have not taught this course before anywhere else. So I would like this class to be a to and fro conversation. There could be things that you might find not very convincing, and let me know, and then we can discuss on how to develop that idea better. And also, once we have a basic understanding of how to approach these research questions using our
announcement.
Yes. Okay. So
just a minor announcement that we need to probably change the venue. Let me find some suitable room, and then he will continue till today 10:30 in the hostel. Maybe if you find the alternate venue and think see if the live stream is being done, then maybe we can start the second half at 2. But anyway, you guys all are from my group, you will know. But you two are keep in touch with Pula for Mondays, then we will inform accordingly. Anyway, I will also inform via email. So the rest of the day. So right now you will continue to tell that.
Okay. So the way that I will plan, this is still just a synopsis of what we are going to cover. So I'm not going to go into any material till the second session. Okay, so brainstorming on the open questions, because I do want you guys to appreciate what are the things that are still unsolved out there. After this, I think I'll be done, and then Dr. Shamant will probably take over. In terms of the topics, I will let him speak eventually on what he wants to cover, but essentially the idea is what other topics of fluid mechanics could be relevant to our understanding of this, of solving problems from this particular area. So I'll keep that empty for now. Now, in terms of the reading materials, I think I have uploaded some books on the cloud folder, but let me just note down the names of the books over here. Number 1, The Mechanics of Inhaled Pharmaceutical Aerosols by Warren Finley. So if you guys access this book, you will see that he tries to develop the basic mathematics of this kind of system before going into the pharma part. So understanding the basic physics is quite useful in general, and this book is a good resource for that. The second book is Biofluid Mechanics. By P. Nithirasu. So in this book, I think this is still an unpublished ebook which is available from some sources. If you want to access this book, if I have not shared it, just send me an email and I can share it with you. So what he does here is not only respiratory mechanics, but also cardiovascular mechanics, mechanics of blood flow, etc. And especially if you're interested in those other bio problems, I think this book is going to be a good resource. Okay, finally, these lecture notes, I think would give you a good start in understanding problems like this. So especially if you work on topics like this, I think the material that we are going to cover would be useful. And then some research papers. I have uploaded the research papers on the cloud folder. We are going to study some of them during this course. I'm not going to study them, I have already studied them, but you guys need to study them. Based on how much we proceed till the end of today, I will probably keep a paper to read for you guys tonight. And the reason why I want you to read, you will gradually understand as we go forward in this week. and there will be 2 more papers on the computational side. The one today, the view from today is mostly on the theoretical side. So the research papers are on cloud as well. I should not go into more details because I think with the live streaming, I want this course to be a complete one, so I will briefly touch upon this overall structure of this course in the second session, and then we're going to go into the derivations. So therefore, let's wrap it up here now.
Okay.
But whatever I talked for the last 20 minutes, I'll just touch it upon for 3 minutes, and then go into the rest of the material. But as we wrap down, any questions from you guys in terms of what would be best in terms of teaching this material or structure like this works? Are we going to come back to this room, or is this it for this room?
Here I think the internet is not possible to set up that.
Okay.
Like what you can do is after the this session, there may be some software session.
Yeah.
We look for let me ask the academic section, are there some rules in the lecture conference or some else where, and then by setting up I guess it will be sorted out.
Okay.
There is one room right in the department beside our engineering drawing room, another extra room. It is generally not used, but there are projector and all these things. And LAN also should be there.
And Wi-Fi will be there.
Oh yeah, Wi-Fi will be there.
Because we will need that for
Yeah. So Wi-Fi will be there. So let me just check. If it gets sorted out, we can start at 2 or 1:30 just in case. You can have an arbitrage.
So at worst, I would not let him teach on the field day. So
Yeah, that is fine because you have come all the way from US. That is not an issue. It is fine. So better go slow and get the things which are to be communicated in a proper way instead of rushing through everything.
Sure.
So
Sure.
yeah.
Okay, so let's run down now.
Yeah. And for the time being, maybe you all can form a simple WhatsApp group and just any change you can readily communicate. Okay. So that's all for this session.
The one with the walking, just make sure that the cloud server folder is shared with them. It will be easier for them.
Yeah, I will just share whatever materials you have shared.
Yeah.
We'll share the whole thing.
Hopefully the projector will be.
Ulal, you will come here or
Here, I will hold.
Achha, it will follow. तो चाय के बाद इनको देखते हो उनका प्रोजेक्टर नहीं है लागत है 10 मिनट लगा हुआ ड्राइंग का नेक्स्ट
भाई पूरा 155 नंबर में चल रहा है गल कराना
हेलो एस 105 है फर्स्ट फ्लोर पे सुपर एकेडमी ब्लॉक। यहाँ पर प्रोजेक्टर मतलब ब्राइट नहीं, थोड़ा ब्लड टाइम लग रहा है, क्लियर नहीं है। हाँ, और यहाँ पर 11 बजे से क्लास स्टार्ट है, तो उसके पहले ही आ जाइए, सही कर दीजिए इसे। फिर हाँ हाँ आ जाइए, 11 बजे से क्लास है, तो आप अभी आ जाइए। हाँ। हमें तो ये नया है, मुझे समझ नहीं आता।
यस रिव्यू में ऑडियो ठीक कर रहा है।
वो कैमरे वाले माइक से आता है तो थोड़ा डिस्टर्बेंस रहती है, जैसे कोई चेयर्स की आवाज़ आ गई, डोर की आवाज़ आ गई, वो क्लियर नहीं रहता है, इसलिए मैं माइक प्रेफर कर रहा था, बट शायद अरेंज हो जाएगा।
ওয়াশরুমে এমনি খুলে আছে, জাস্ট এখান থেকে বেরিয়ে ওদিকে তাকালে লাল দরজা, জাস্ট বেরিয়ে ওয়াশরুম আছে, চারদিকে
मुझे भी 5-10 मिनट लगे ढूंढने में।
हाँ
मुझे 10 मिनट लगे ढूंढने में।
हाँ,
आज उधर गया तो उधर गया।
डायरेक्शन किसी जगह दिया है, पर अंदर सब लैब और क्लासरूम ही है, तो दरवाजे के बाहर वॉशरूम।
देखो साइन लगा देना चाहिए ऐसे ही।
हाँ, एक साइन देना चाहिए किसी जगह।
आप एयरटेल का यूज कर रहे हैं क्या
हाँ
ऑनलाइन के लिए?
हाँ।
अच्छा अच्छा, पर आपका डेटा कितना है इतना तो?
ये मेरा पोस्ट पेड है।
अच्छा पोस्ट पेड है।
ये इमरजेंसी के लिए रखा है। वैसे जियो भी है पर जियो में नेटवर्क कम दिखा रहा है यार।
हाँ
जियो
जियो।
में मैं कम यूज़ करता हूँ।
आपकी जो वीडियो है कैसी चल रही दिखा दें?
अभी तो सिर्फ यही आ रहा है।
अच्छा
थोड़ी पीछे करके देख सकते हो।
माइक भी नहीं है।
अब माइक का ही प्रॉब्लम नहीं है। मैंने बोला सर शायद करवाएंगे कुछ करेंगे। दुकान की तरफ से मुझे क्वालिटी ये क्वालिटी के बता रहा हूँ।
अच्छा 1080 तक है माइक की।
बस माइक का है क्योंकि इसमें नॉइज़ आ जाती है साथ में। जैसे ये एसी चल रहा है उसकी नॉइज़ ले लेगा, दूर की ले लेगा, चेयर्स की ले लेगा।
आप लंच ब्रेक के टाइम ये क्या सब पैक करके लेके चले जाएंगे या क्या करेंगे?
यहीं पे रहेगा। उसके बाद लंच के बाद यहीं पे होगा।
हाँ हाँ, यहाँ पे ही होगा।
लॉक करवा देंगे सर।
वैसे तो हम वैसे छोड़ देते हैं
अच्छा,
बंद
अच्छा।
करके सेटअप 5 दिन तक।
लॉक, हाँ लॉक करवा कॉल
लॉक
करेगा सिक्योरिटी
गाइड ये गार्ड को बोल देंगे।
अच्छा गार्ड, ये गार्ड अच्छा,
हाँ
क्योंकि फालतू में आपको कैरी नहीं करना पड़ेगा फिर से इधर उधर।
शाम को भी मैं सिर्फ लैपटॉप लेके जाता हूँ बाकी
अच्छा
अच्छे
अच्छा,
से।
ओके।
तो बार बार
तो हर सेशन का अलग अलग वीडियो ऑलरेडी आपके पास है ना, तो मैं अपलोड कर दूंगा।
अब वो मैं लेक्चर वाइज कर देता हूँ ना सारे।
हाँ
आप जो शो कर रहे हैं वो तो ये ज़्यादा होगा ना।
ये उसमें बंद की है स्क्रीन में। ये पिछले वाला दिखा रहा है।
वो वाला दिखा रहा था कि ये वाला?
ये वाला दिखा रहा है।
चलिए ये तो सही है।
अभी ये अभी देखोगे तो अभी ये आ रहा होगा।
नहीं नहीं, जब आप वीडियो शेयर करेंगे उसमें यही दिखा रहा होगा ना?
उसमें ये दिखा रहा है।
नहीं मतलब अभी की बात नहीं कर रहा, जब आप वीडियो चलाएंगे तो ये
हाँ हाँ, ये वाली स्क्रीन में चेंज करता रहूँगा ना। जैसे
अच्छा।
कई बार ये फुल स्क्रीन कर दूंगा, कई बार ये कैमरे का व्यू ये फुल स्क्रीन कर दूंगा। तो वो
तब तो दिख रहा है सर,
हाँ
है ना?
हाँ। अभी शायद बीच बीच में चेंज हो जाएगा अगर मैंने किया होगा तो। कई बार वो दे देता हूँ। इनमें से मतलब कोई भी दे सकता हूँ।
Let's start again. So that was the brief overview of the structure that hopefully we will be able to follow through. Let's go into the first topic for today, which is, as I said, motion of a single aerosol in a fluid. Again, let me know if my handwriting is outside the screen. Again, I tend to use both particle and particulate. I personally like the word particulate a little bit more because the simulations that we run and we are going to run in this course, we model them as inert particles. On the other hand, it is understood that they are made of liquid. So I like the word particulate more than particle just to carry that sense that it is still liquid particles. Now, as I said, we want to first develop a mathematical understanding of the motion of a single particle or a particulate. Now, first, let's think about what we can achieve from those mathematics and what are the assumptions that would go into developing that mathematics. The context over here is we want to develop an understanding of aerosol dynamics within a complex domain. Like the human respiratory tract. And we are going to model the deposition mechanics within the tract. We are going to simulate the process. But we are going to first start with it being a single particle motion. So much of the aerosol mechanics can be theorized through understanding the motion of a single particle. And to understand the motion of a single particle, we need to figure out the forces, the trajectories of that particle. So we get the trajectories from the corresponding equation of motion. So the idea is to be able to develop the equation of motion for that particle. So forces and equations governing the motion of a single particle moving through a fluid. And while developing those equations, we are going to apply the appropriate assumptions in terms of different aspects, like what kind of Reynolds numbers, Stokes numbers, Rolle numbers we might expect in those domains. And that particle would be a small, rigid, single particle moving through air. So every time I say the word fluid, in this case, because we are trying to study breathing and inhaled particle transport through our airway, that ambient fluid is going to be air. So the problems that we are going to solve, we are going to use the material properties for air. Now, while developing the equations, the two main assumptions that we are going to use would be this. Number one, the particles are going to be assumed to be spherical, which is a good assumption most of the times. But if you look at recent literature, people are also looking at what happens if they're non-spherical. The good thing is, in terms of the regional deposition trends, even if you consider them to be non-spherical versus spherical, it does not make much difference. So if you are trying to apply your fluid mechanics knowledge into understanding infection mechanics, into understanding targeted drug delivery, it doesn't make that much of a difference. So that's number one assumption. The particles are going to be assumed spherical. Number two, we are going to assume that the density of these particles, the material density, is much, much higher than the density of the ambient fluid or the ambient air. So let me write those down. So the two main assumptions in respiratory aerosol science. Number one, the particle is assumed spherical. And as I said, this, in terms of when we are trying to apply the knowledge to a practical problem, this is a fairly reasonable assumption. So this is usually reasonable. Number two, the density of the particles is much, much greater than the density of the fluid, which in this case is air. Now, this also is quite reasonable most of the times. Because if you think about drug delivery, what do you think the density of those particles are for drugs? For nasal sprays, nebulized sprays? Slightly above water. Most of the times it's very close to water. So 1000 kg per cubic meter, and what is the density for air? So it's much, much greater than the density of air. What about infection transmission? What about those particles? So if so how do we infect others? So we eject this particulates that are sheared away from our mucus. Initially, if you think about the fluids in our airway, it's mostly water, and then the moment it goes out into the air, it undergoes some environmental dehydration. It actually loses the water, becomes even denser than what it was inside our airway. So it is, of course, going to be much, much dense than the air. But can you think about a situation where this assumption might be sort of questionable, that the density of the particles is not probably much, much greater than the density of air? So someone, yeah, go ahead. Yeah. So someone said that aerosols are things that stay airborne, right? Rather, it's more accurate to say that after those ejector particles lose all the water, those gradients, which are the single virus particles, they stay airborne for hours. Now, those variants are not spherical, so forgetting the first assumption, they could be much, much light. And the density of those variants could be comparable to that of the air. So that caveat is still there if we are trying to think about a single gradient. In our course, or for that matter for most of these kind of inhalation studies, we assume that those variants are embedded in liquid particulates, in which case the density of those whole particles could be assumed to be much better than that of air. So hopefully I'm going to comment on this later on in this week. We'll be going to the infection transmission part of the course, but for now we're going to assume that rho P is much better than rho fluid. So let me just write down the comments here, but exceptions could be there. For example, micron scale, and for that matter, sub-micron scale, airborne virus nuclei. And we'll comment on this later on. However, for our purposes, for now, we are going to assume that typically if you track the order of magnitude difference, rho vertical is 10 to the power of 3 of the rho fluid. So as a result, we do benefit in terms of the forces from the fluid that we need to consider in our equations of motion for those particles. So which force do you think should be considered? What is the main force contributed by the fluid? Huh?
Van der Waals forces.
No. Van der Waals forces is a molecular, intermolecular. Huh?
Gravitational force.
That's a field force. I'm talking about the fluid force. What is the main force that is used? Drag. Drag is the main force that is going to dominate over all the other forces. So the result of assumption 2 is drag force on the particle is much larger than all the other fluid forces that may act on it. I mean, they're still there, but in the equation we can ignore their overall effects. Okay? But then again, we have left out this caveat, so let's quickly take a qualitative note of what forces could have been there before we go into the actual equation. So however, if the rho particle is of the same order as the rho of fluid, several fluid forces like Magnus force. So this is the lift force that is generated from a surrounding fluid field on a spinning particle. Bassett force, pressure forces.
Sound it looks out of the slide. Now it's
If I move the page, it does focus a little bit. Facts and correction. Virtual mass effects. Would become prominent. Now, based on your problem that you're trying to solve, you might have to include some of these effects and perhaps something here. In the simulations that we are going to run, along with the regular drag and the gravity force is still there, it's a field force. I do include the Safman lift force because Safman lift force is specific for particles that are very small and they act transverse to the direction of the particles. So since we are trying to track radial drug delivery, I do include that lift force into the numerics. But I'm not going to include that in the equations that I'm going to develop because its contribution is anyways very negligible compared to the drag force. So including all this is fine, but that would make the analysis much more challenging. So for our purposes, let's hold on to assumption 1, particle is spherical, and assumption 2.
What will be the Magnus force and basic force?
So the Magnus force is on particles that are spinning, it's a lift force.
So, like, have you studied the potential for chapter? In that it is discussed, like, there is a uniform flow, in the, like, a cylinder is rotating, and there will be, like, that kind of force. So,
And yeah, if you want to discuss details.
but you can maybe after this session, the question answer round, you can.
And you can just look them up as well, because knowing these forces, what they quantitatively mean, is important, especially when you are trying to solve an unknown, unsolved problem and you don't really know what are the different effects that could be. For now, we don't need to worry about them as long as the particle density is much higher than the density of air. So with this, let's go into the main dominant force that we do need to encounter, which is the drag force. So, assuming the drag force is negligible, fluid force on the particle and the only we can write down this very basic equation of motion, which is m dv dt is mg plus f drag. So of a single particle. And something that we have known since our high school days. And whatever else would follow would be based on these equations and how we can ignore or place certain assumptions on the different terms. Now to solve this equation, we do need to solve this equation because we want to get the particle trajectory, right? So we need to solve for the velocity, and integrating the velocity, we get the trajectory of the particle. So to solve this equation, equation for v as a function of the time t, we must determine the drag force. No drag divided by half rho fluid so what is that V rel? It is the relative velocity. A is the cross-sectional area of the spherical particle. So if T is the diameter, so pi square root 4. And for that matter, if we had ignored the first assumption, this is where things start to get complex. We need to know the profile of the particle if it is indeed non-spherical. The V rel, V relative is V bar minus V fluid. We are solving for V, which is the velocity of the particle, and the resting velocity is V fluid. Okay, now with this being true, this is the CD, fine. What is the direction of the drag force? The direction of the drag force is opposite to the relative. The drag force acts opposite to the velocity of the particle relative to the fluid. So let's write the drag force down hence. So F drag is minus half rho fluid V well squared pi d squared over 4 Ct, the unit vector for that relative velocity. So write the unit vector V rel is okay, and the negative sign accounts for the fact that it is directed opposite to the motion of the particle. The drag coefficient CD depends on the particle. So that's why I'm trying to take this V well as the velocity in the Reynolds number formalism. So this is the kinematic viscosity. This Reynolds number with the drag coefficient CD, there are some empirical relations. So to connect RE and CD have very small diameters d and low velocities v well. Typical Nessel press, the median diameter is anywhere between 30-40 microns, but they can go as high as 500. Okay, so we are going to use this expression for CD, 24 over RD, and this is for RT less than 0.1, which gives a CD within 0.1% error. Okay? So now I'm going to plug this CD into the formulation that we had for the F drag. By the way, I use this acronym PTO a lot, which as Indians we know that it is turnover. So once I ask so I've been using this for a while in my classes that I teach at SJSU, and once I asked my American students, do you guys know what is PTO? Can you guess what they thought it is? Paid time off. So they thought that I'm giving them paid time off after increasing the budget. There is one space. So I had to tell them that no, we are referring to our former British masters that please turn over the page. Okay, so let's call this equation 3, and the equation numbers are going to be difficult to keep track of eventually, but since we are going to connect different equations together, but this is equation 3 for now. So F drag is that equation, and we are going to use that. So therefore, from equation 3, the F drag is minus half rho fluid V well squared by d squared over 4, 24 over RE, so I'm breaking the Reynolds number up, kinematic viscosity divided by V well times d, and the unit vector for V well. So let's simplify this a little bit. So we have 2, 4, so this becomes 3. We have 1 V relative over here, so that cancels the square. And what else? The D gets cancelled here. So F drag is this 3, so minus 3 pi. This nu could be broken up as well, so if I do that, nu d v minus v fluid, I'm writing I'm combining this vrel with the unit vector for vrel to write it in the vector form, and I've used mu as the rho fluid times. So we have seen this equation a lot of times in fluid mechanics. What is the name of this equation? Stokes law. So this is valid for particle diameters that is greater than the mean free molecular path. So in air, that mean free molecular path is, anyone wants to take a guess how small that could be? It is 0.067 micron. So when I said 0.1 micron is probably the smallest particle that we typically need to consider, we can still have this assumption true. So in air, at typical breathing conditions, this mean free path distance is 0.07 micron, actually 0.067. So this gives the Stokes law, but before we start solving problems, let's think about a few other effects. We can have a particle that is not really moving, it is trying to settle in the fluid, and that leads to the regime called settling mechanics. So we are going to study that. And then sometimes the particles are trying to move with respect to the fluid. They are moving fast, and there comes the concept of the inertial dominance of the particle's motion. So we are going to look at that kind of inertial mechanics as well, which leads to inertial sedimentation. So both gravitational sedimentation, settling, as well as inertial impaction. So let's try to derive the equations for that. In terms of our timeline, let's continue till noon, and I'm going to ask you guys if you want to continue a bit more. But let's try to cover most of the mathematics that I wanted to cover by end of today. Any questions before I move on?
Otherwise, we'll meet at 2. So try to be like initial lunch between assemble their devices.
Okay, so from here we're going to go into the concept of settling velocity. Do keep track of the equation numbers before we move further. So this is going to be equation 4, which we are going to use later on again. So particle in stationary air will settle under gravity and reach a terminal velocity quite rapidly. And this process has a specific name, it is called sedimentation. So if we are to develop the equation for this process, the process of sedimentation mechanics, we are going to again start from the very basic equation of motion that we started out with before. So since the velocity in the equation, which is m dv dt is mg plus f drag, we can ignore this particular term. That velocity, the change of velocity is 0. mg would be equal to the f drag. The vertical force plus the Reynolds number to be much small. Again, to be much small. Again, even I got confused with the Reynolds number. This is not the Reynolds number of the fluid. This is the Reynolds number that we are talking about of the particular form. So the F drag. So let's apply this directly over here. So equation 4 F drag. So equation 4 F drag becomes 3 pi mu.
Equation. Isn't always negligible when we talk about added mass forces also?
It is not always negligible. What we are assuming is this particles at this length scale, that is being much greater than the density of the surrounding fluid. Mu dv settling. If I miss any term, because I'm going to do it by hand, just shout out if I miss anything. So rho particle for velocity by dq over h. Rho particle, this d settling in room temperature air. We need to know some of the material properties, but as a side material properties, this compound's material density is, so the specific gravity is 1.26. It's 1.26 times 1000. The viscosity of air is what you need to know is 1.8 times 10 to the power of minus 5 kg per meter second, and the density of air is 1.2 kg per cubic meter. So we can directly apply the formula that we had derived. The particle settling in stationary air, we have V settling is rho P V square G over 18 mu. So let's put in the numbers here. So the rho P is 1.26 times 1000 kg per cubic meter. The D is given as 10 micron. So 10 times 10 to the power of minus 6 meter squared. And G is divided by 18. Mu is given 1.8 times 10 to the power of minus 5 kg per meter second. I have double checked the dimension, but it should be fine if you do the calculation. If you had calculators, anyone has calculator here? So do the calculation, because I want my work to be double checked as well, because my answer will be wrong. What I have here is 3.815 times 10 to the power of minus 3 meters per second, or 3.815 meters. So if that is the velocity of the particle of settling, then we can directly put it into the Reynolds number formulation to get the Reynolds number, which is what this problem had asked us to find. So therefore, the particle Reynolds number is V settling d over mu by rho air. So V settling is 3.815 times 10 to the power minus 3 meters per second. D is 10 micron. Mu is 1.8 times 10 to the power of minus 5 kg per meter second, divided by the density of air is 1.2 kg per cubic meter. Again, you should double check the dimensions, but I'm pretty sure they are fine over here. So this number should come to 0.002543 if you double check the number. So folks who don't have calculator, this
So when you are calculating the Reynolds number of the particle,
yeah.
we are considering the viscosity and the density of the
Yeah.
surrounding medium,
Yeah.
not the particle fluid.
And that's what threw me off while I was preparing the material, because that is what is going to control the motion of the particle, not the properties of the particle as such, beyond the density, because it's non-deformable, because it is inert. And at that point, I think I have some material on that as well, because if you do think about the viscosity of the particle, there is a particular term that we have already used that gets revised. That term is the drag coefficient. So I have some notes on that as well, which I think you are going to touch upon today at some point. So this is 0.0025, which is much less than 1, which tells us that the assumption that we had started out with is still valid. So therefore, we have used the settling velocity formalism quite justifiably. Yeah, so if the numbers change once you do the double checking of the numbers, just let me know. Questions? So the next point is actually connecting back to what you just mentioned. Until now, we are assuming the viscosity of the surrounding fluid, right? While getting all these numbers. In other words, we are assuming these particles to be solid and inert. What if they are not? What if we do need to consider the viscosity? So what gets corrected in our equation? So let's take a look at that. So the formalisms until now were for solid spherical particles. But if they're not solid, the fluid wrapping the particles around the particles can create an effect called internal circulation. Anyone has any experience with that kind of mechanics? Circulation inside droplets. So, so that effect does change the overall equation. So let's take a quick look at that. So however, if the particle is not solid, but is instead a liquid particulate, it is possible for the relative motion of air flowing past the particulate to induce internal circulation so that would change the overall effect of the drag. So let's take a look at that because of this internal circulation. But before that, since we are trying to approach respiratory biomechanics over here, can you think about a particular situation where this would be valid? Or where this particular nuance could be very critical to the physiological function of that process. That the particles' internal circulation of the fluid material inside is very relevant. It actually happens in the alveolar sacs. So as we inhale air in, when the particles go to that kind of length scale, there the internal circulation of the particles is quite critical to the exchange that is happening, the gaseous exchange, everything. So there's a group in Israel, I'm going to touch upon one of these papers later on. They are looking at that effect. So basically they are 3D printing the entire lower airway branch model. They don't consider it to be a 3D structure anymore. They're basically including certain layers of branching, certain generation of branching, a 2D 3D printed model, but they're looking at that kind of internal circulation in the particulates that are in the very fine particle channels. Okay, so if we do have this kind of liquid particulates where this effect is prominent, let's see what happens to the settling velocity as a result. So settling velocity for liquid particulates the internal circulation lowers the drag force effect and increases the settling velocity compared to that of the solid spherical particle that we have studied until now. So compared to a solid sphere, of same size and density. And along with this internal circulation, if you think about liquid particulates that have some internal contaminants, their motion can make the process even more challenging to track. So note the surface impurities in liquid particulates can make the mechanics quite challenging. Okay, now let's focusing back on what changes to the drag force because of this effect. This equation was derived by Hadamard and Rimsky. So F drag is 3 pi mu d v rel times 1 plus 2 mu of air by 3 mu of the particulate divided by 1 plus mu of air by mu of the particulate. Now if you think about this correcting cofactor that is coming in, if you do put in the numbers, you will see that in our purpose, it becomes close to 0.994. So it is okay to ignore it most of the times. But this is what happens if you do want to include the viscosity of the particulate material into your equation. So this factor So this is the factor that is extra for water droplets. In air, it is close to 0.994. So the internal circulation effect could be negligible for the problems that we have been studying. No time. Do you want to continue or stop for now?
Okay, not saying.
Even
So
if-
stop for now, like then again we will meet at 2. But you can like ask him regarding this session if there is any query.
Okay, let's stop for now. Your professor wants me to stop for now. So let's stop.
Let's go slow today. Pick it up on the coming 2 days, 3 days.
Any questions before we stop? No? Okay, so when do we meet again?
2 here will be.
And 1 atmospheric pressure. This lambda Fp is around 0.067 micrometer. Now, is this a good enough assumption? Well, as I said, it depends on the problem that you are trying to look at and the particle sizes that will be relevant for that problem. So for example, for drug delivery, if you are applying some kind of formulation with the particle sizes that are geared towards the smaller end, you might have to be careful about using these assumptions. Similarly, for infection transmission, if you are looking at particles that are sub-micron, there could be some that are suspended in air, you need to be careful about that. So, while pharmaceutical particles or aerosols typically start from around 0.5 micron, the inhaled pathogens, some inhaled pathogens could be much smaller than that as well. And closer to even this lambda FP. Now, what happens if we do need to consider those so-called very small particles? So let's check what kind of correction we would need in our formulation if the particle sizes get smaller than what we have been using. So we need some correction factor. It is called the Cunningham slip correction factor. So with the Cunningham slip correction factor, revision. Oh, sorry. Yeah, so let's call that Cc. So that Cd, the drag coefficient, is now 1 over Cc times 24 over Rd, what it was before. So therefore, the drag force just gets this extra factor Cc in whatever we had before. And of course, Re is still much smaller than 1. And following the same line of calculations as we did before, we can figure out that the V settling in this case would be Cc times rho particle d squared g over 18 mu. So this is the correction to equation 4 on our lecture notes. Now there should be a way to calculate what is this Cunningham slip correction factor, and it is a function of the mean free path. So the approximate formula for the correction factor is Cc is 1 plus 2.52 lambda Fp divided by d. Now, if you apply the length, the actual value for the lambda over here for the typical particle sizes that we are looking at. So, for example, if we use for d greater than 0.1 micron, if you apply lambda to be 0.067, you will see that this becomes very close to 1. And we're going to use some numbers in the problems that we're going to solve next for this. But in general, as you can see, this because of this component over here, Cc is always going to be greater than 1. As a result, the V settling width for small particles is the velocity is larger than the settling velocity for the particles that are slightly bigger, and the other way around, the drag force here is smaller than what we had before. Okay, so with this, let's solve another problem. And do we have more calculators in the room? Or okay. So from now for the examples, I would probably go a little slower so that you guys have time to do the calculations. Okay, so evaluate the settling velocity in air for a 0.5 micrometer diameter spherical droplet of nebulized Ventolin respiratory solution. So just for our knowledge sake, let me write down what this compound formulation is. So this is 2.5 milligram per ml of salbutamol sulfate and 9 milligram per ml of sodium chloride in water. So calculate the settling velocity in air for this sized particle both with and without this Cunningham slip correction factor. Okay, so in terms of the given parameters that we would need to know, the viscosity of air is, as before, 1.8 times 10 to the power of minus 5. So let's start with the solution. And we have just derived the formulation for the settling velocity. So V settle is Cc rho particle d squared G over A. Okay, do we know all the information here to apply this formulation? Lambda and the D, right? The lambda, as I told you, although I have not written down in the problem statement, we know that value for air. The D is known. The mu is known. Do we know the density of the particle here? We don't. So we have to assume something. So based on the compound, and this might be something that would be unknown to us engineers, but we can assume based on the nature of the compound, this is very close to a water-like solution. So let me write that down. So presuming that the pharmaceutical agent and the salt have negligible effect on the solution density. We can hence apply the different numbers into the formulation. So Cc is something that we are trying to find, evaluation settling velocity. Okay, Cc we don't know yet, so let's keep it like that. The rho particle is 1000 kg per cubic meter. The diameter is 0.5 micron, so 0.5 times 10 to the power of minus 6 meter squared times G divided by 18, 1.8 times 10 to the power of. If you do consider the effect of the slip effect or not, the settling velocity just changed by quite a bit. So the settling velocity increases by It is 0.01 minus 0.00757. If I write the first velocity in millimeters per second, so it would be 0.00757 millimeters per second. So which, if you calculate, will be around 32%. So it changes by quite a bit just by doing the slip. Now, what is the driving factor over here? Because if you think about the 0.067, that's fixed for air. So that means that if you have smaller particles, you need to be careful about whether you want to include that correction or not, and you probably need to include that correction. And hence, for very small particles, we do need to include this into our mathematics. Okay, so until now, including this problem, we have been talking about how in stationary air particles would settle. Now, what happens if the particle is actually so fast that it is moving with respect to the fluid and there is a strong component of inertia in its motion? And that inertia, think about the particles. Let's again assume a drug delivery application for it. So, as we spread the particles, the initial speed of the particles is quite high. Anyone can guess what the initial speed of these particles are as they come out of the spray nozzle? It's on the scale of 10 meters per second. Very high. So, based on the size of the particles, their inertia is quite strong. And many of them, they actually land in the very outer part of the nose. So if you think about this 3D print, many of these particles, they would end up right over here. And then they move with the mucociliary stream further down the tract. So the initial impaction, which is what is happening then, is quite important, especially for drug delivery applications. So let's take a look at that. Yes?
Like in this last problem, we have the density same as that of the surrounding medium. So
We did not, we took the density as water. We did not take the surrounding medium is air. So over here, so this is where we took the density, right?
so we just approximate it.
We approximated it to be water. The surrounding fluid is air, so we did not take it as same as the surrounding fluid. So these are little water particles that are moving. So think of you are applying it inside your nose as you're breathing. But your question could also be, is it realistic to assume it to be a water-like solution? So that's a good question because this has a chemical compound, it has sodium chloride salt.
Is there a higher settling velocity or lower? Or like what is the motivation of changing the fluid density? You were saying like 1000 to 1500 you are doing.
The settling velocity is important depending on how the nasal spray is hit. Because if you are directing the nasal spray, so is there a shock here? Let me just.
There is this chalk box, the white one.
Just
That
give me
corner. Maybe the black pen also you can. Marker pen is there.
Okay. So this is just a quick diagram. So basically, if this is the nose, and if you are holding the spray bottle like this, so these particles they go up. Now let's assume that the particle comes to the velocity dies down and it's trying to settle in stationary rate. Then if it is trying to settle, for example, over here, like this, if this is a target site that you really intend it to be, then it is useful, right? But if it is not the target site, you want the particle to reach further back in, then this settling is not useful. So whether the settling mechanics is useful for a drug delivery application, that depends on what your target sites are. And as we are going to see in a couple of days, the target tissue sites are preferred for different functions. Yes.
I have never used this kind of thing, but is there for a particular setting, can there be different targets, or is this mechanism usually targets the same place?
There could be different targets. So, for example, let me show you some pictures over here. So this is something that we are going to see later on in this module. So this is a respiratory area that is built for CT scans. This blue region over here, it's called the nasopharynx. It is where the two sides of the nose merge together. So when you get a cold, for example, that sore throat sensation that you get is basically over there, because that is the trigger site of many infections. So that is one particular target site for some of the pathogens. But is it so for others? Not really. So for example, there could be a pathogen that mostly infects this anterior part. Or for example, even pox family viruses, because monkeypox is out there, so we are working on that as well. They actually start out further downwind. Now what this nasal sprays can do, it actually cuts through that target site. This is where we want to send the drugs, because that's what the infection is. Well, this is according to the instructions that come in the back of the product. But typically you do improve a lot just by a different way of wording this. Anyway, so these are some of the papers that we should be studying owing to particle inertia. So, as I think I already on certain parameters, so let me write down some comments before I try to develop the mathematics here. So besides sedimentation, which in our application would be always under gravity, another important mechanism that can cause inhaled particles to move relative to the ambient fluid and deposit on the walls is particle inertia. And sometimes it works to our benefit, sometimes it doesn't. It would work to our benefit if the target site is such that the inertial motion of the particle would direct it over there. But otherwise, we have to think about other ways to send the particles. If it is a drug delivery application, if it's an infection mechanism application, then the questions are different. We need to know the particle inertia properties to figure out how much of the infectious load would reach the infection-prone sites along the airway. Either way, we need to understand how the inertia impacts the trajectories of the particles inside the airway. So, to assess whether a particle will deposit by impaction, we again would go back to the same equation. So m dv dt is mg plus f drag. Now, over here, what can we ignore? So, first of all, now that we are using this equation where we are going to isolate just on the inertial interaction, we are going to get rid of the second term on the right hand side. So, we are going to get rid of the gravity effect. We are going to use the f drag formulations that we had before and see what we can derive from here. what we are going to see is there is a specific time scale of particle relaxation time that we can use to characterize the mechanics, and that is something that is going to help us to non-dimensionalize all these equations as well. So let's try to do that. So this is to assess the inertial dominance. So dv dt is g plus, we are going to use the f drag, so this comes from the equation that I have, divided by m. So let's try to simplify this a little bit. So dv dt is equal to g minus 3 pi mu d v minus v fluid by cc by, this is 4 by 3 pi d cube over 8 rho particle. So let's now cancel the different terms that we can cancel. So sorry, this is cc. So this becomes 18, the pi's get cancelled, the d, one of the d's would get cancelled as well, so this makes it d square. So the 18 factor comes from here, so 18 mu divided by d squared rho particle, rho p, rho particle, and then the cc correction factor is here. This multiplied by v minus v fluid. Tell me if I miss anything here. So 18 mu divided by d square rho particle cc v minus v fluid. Okay, what is this particular term? So this has a special name, or the inverse of it has a special name. So this I can write as dv dt is g minus 1 over tau v minus v fluid. So this tau over here, if we check the dimensions, it has the scale of time, and it's called the particle relaxation time, which is going to come back again in our material soon. So let's name this particular equation. So let's call d square cc over 18 mu. So this parameter tau is the particle relaxation time. And let's call this equation 10. And this tau would be useful, as I said, when we normalize these equations. Any question, Abdullah?
What is the critical meaning of this particular relaxation time?
What is what?
Critical meaning.
Physical meaning of the particle relaxation time. Can you tell me, based on this equation, what you think would be the physical meaning of this? If you don't have the g component, and if it is stationary fluid, so it becomes v over tau, right? So dv dt, so that gives a direct sense of what the particle velocity would be like, the time scale of that velocity, to compute it, if it is a stationary air and if it is falling through that. So that is one way to think about the physical nature, but you can think about it in terms of other non-dimensional numbers as well. So I'll come to that in a moment. But this term by itself, it is very similar to Stokes number as well. So Stokes number is a non-dimensional particle relaxation time in certain sense. So you just need to add some terms, cofactors to this term, and it will become the Stokes number. So there is that way to describe it as well. Or you, as I said, you could use this expression to describe what the frequency is.
So is it the time that particle takes to catch up the fluid velocity?
That is one way to think about it as well. So if you put a particle which is initially at rest in a moving fluid, the time it takes to reach that velocity. Or if the particle, if the fluid is at rest and the particle is moving, the time it takes to come back to that state of the fluid. So both ways it would work if there is a difference in velocities. Okay, so from here we are going to use this tau, but let's define a few other mean terms that we can use to non-dimensionalize these equations. So let us now, so we are going to use this equation 9 for the non-dimensionalization. So let us non-dimensionalize equation 9 using u naught. So u naught, you can think of it as a velocity in the fluid medium where you are trying to study the particle transport. So if you think about particles moving through the airway, if you are just looking at the upper respiratory tract position, it is a u naught, which is true for the upper airway. But rather, if you are trying to look at what is going on further downwind in the bronchial region, it could be a velocity that is in the near the alveolar sac. So it is dependent on the problem that you are trying to study. So u naught is a typical velocity in the fluid flow. So u naught is a typical velocity in the fluid field along the respiratory pathway. So it could be, as I said, depending on the problem, at an appropriate region along the respiratory tract. We need a d. It is a typical dimension of the geometry along the respiratory tract again. Now, the geometry of a respiratory tract is quite interesting. It covers quite a few orders of magnitude. So it starts from on the scale of centimeters and reaches near the alveoli, which is approximately around 100 micron on an average. So it starts from centimeters and reaches to microns. So as a result, if you think about this d, the d itself can vary a lot based on which region of the airspace you are trying to study the transporting. But whatever the typical value is what we are going to use in the problem. So let's use this u naught and d to on the equation 9 that we have derived in the previous page. So we will couple u naught and d to go to a characteristic time scale. D over u naught. So let's put that into equation 1. Therefore, in equation 9. So equation 9 is this. So if we non-dimensionalize this v, so v divided by u naught by dt divided by d over u naught, and to adjust we put u naught for the other u naught here and d over u naught. This is equal to g minus the V bar is non-dimensionalized with respect to U naught, and the V fluid is also non-dimensionalized with respect to using U naught. So as a result, this becomes U naught for the correction and then a tau. So this is what we have. So let's now use this particular form. So from here, let us now introduce some new terms instead of using this particular formalism for the velocities and the times. So subsequently, let us introduce the following non-dimensional variables. So V bar prime is V bar over U naught. Then we need a V bar fluid, which is V bar fluid over U naught. We need, if we want to use the V relative formulation, we need that as well. So V rel prime is V bar prime minus V prime fluid. What else do we need? We need the T prime as well, which is T prime is T divided by D over U naught. Do we need anything else? We need the G as well. So let's assume G bar hat instead of prime to be G bar over G. And let's call the equation before this as equation 11 on my lecture notes. For the chronology of the equations, do follow the lecture notes that I've posted. I might be missing some of the equation numbers that I write here. Okay, so let's now plant all these dimensionless variables into equation 11. So equation,
The last variable on what is this? This is the G.
the G.
So this is non-dimensionalized with the magnitude of G or
With the magnitude.
so you need vector.
Right. That's why you're using the hat. Okay, so we are calling this as equation 11. So this equation 11 using this terms that I just introduced would reduce to would now reduce to so we have so the first cofactor is by itself U naught square over D. But this now becomes dV bar prime over dt prime. Then the G becomes G times G bar hat minus U naught over tau by multiplied by V prime minus V fluid prime. So this is what equation 11 is by simplifying the cofactors and putting in the dimensional variables. Let's now try to simplify this a little bit more. So tau times G over U naught times G bar prime minus this particular term over here becomes V relative. So let's block this equation out. Let's call this equation 12. What is this coefficient? What is the second most well-known non-dimensional number in fluid mechanics? Not Reynolds number, it's the Stokes number, right? So this coefficient is equivalent to what we know as the Stokes number. So I'm going to write Stokes number as STK to distinguish it from Thrall number. So STK is tau U naught over D. Let's now plug in the expansion for the particle relaxation time tau that we have found before. So STK is rho p d square cc over 18 mu for the tau part times u naught over d, which is what I was trying to refer to as this is tau and this is u naught over d is 1 over t, t inverse time scale, right? So basically you can think of the Stokes number as a dimensionless portion of the particle relaxation time as well. So STK is u naught rho p d square cc over 18 mu d. Yeah, sorry. So this, let's call it equation 13. Now, what else can we do with this? We have been using in equation 12, if you go back, we have still not left out G, although we are trying to just study the inertial interaction. So we can do something about it, and that can help us isolate more on what is referred to as, or what happens with inertially dominated mechanics. So let's do that. But before that, let's try to think a little bit about this particular formalism as well, what else we can do, because as you can see by now, many of these right-hand sides for different terms, they look very similar. If you go back to the equations that we are deriving since morning. So let's dwell a little bit more on this before we move on to the exclusively inertial conservation of the mechanics. Was there a question? Okay. So now recall that the V settling that we had derived before lunch was Cc rho p d square g over 18 mu. Right? So what we can do here is think about this particular part. So rho p d square over 18 mu. What is that? That is rho p d square over 18 mu. We have just derived that. It is the tau. Correct? So this part itself is tau. And what else do we have? So Cc times tau Cc times tau times g. Let's quickly look at, is that indeed the tau? Can you look at your notes? Yeah. So tau is this. So tau is rho p d squared cc over 18 mu. So tau does have the cc. So we have to adjust for that. So if this is this, then let's write it as V settling is cc. We are going to bring the tau part here, d squared cc by 18 mu. But for that additional CC that we bring in for the tau, we have to add a correction 1 over CC times G. And there should be a mu in the denominator. Yeah. So now I can call this part as tau, but this CC and this CC, they get cancelled out. So what we have here is V settling is this tau times the G. Correct me if I'm wrong. So V settling is tau times G. So let's try to use this in the formulation because of what? Because we still have this tau G over here. So we can possibly use it over there. So therefore, in this equation 12, let's try to apply this. So in equation 12, we have tau u naught over d times dv prime dt. This tau g is v settling, we just found out. So tau g is v settling over u naught times g bar hat minus v relative bar. Let's write this as Stokes number, which is what we already found out. So this is Stokes number times dv prime dt is v settling over u naught g bar prime minus v well prime. So let's block this equation out again. Let's call it equation 14. So this is finally the non-dimensionalized version of the equation of motion of spherical particles moving through a fluid. Well, we have considered all the terms. We have not yet left out the g term, the v relative, the inertial term is still there, and we have everything else that we need in the motion. For a spherical particle. Okay, so now that we have this, we can think about the orders of magnitude of each of these terms based on the question that you might try to address. So let's think about the first case being if the Stokes number STK approaching 0, the left hand side in equation 14 is 0 as well. But what happens to the right hand side terms? So on the right hand side you have V settling. So on right hand side you have V settling, which is, if we again use the formulation that we have derived before, so slip correction factor times rho p d square g over 18 mu. Right? We can rearrange this right hand side of the V settling to see how it depends on the Stokes number. So let's do that. So if I write this as rho p d square cc over 18 mu times u naught over d times d over u naught times g. So basically we have brought in this word. The rest is same as what we had, the g and the u. So this becomes the Stokes number now times d over u naught times g. So if that is the Stokes number, then that implies that if Stokes number is going to 0, this is going to 0 as well. So therefore, the right hand side is in equation 14. This is 0. You just are left with the v relative. So right hand side, or the term 1 on the right hand side. So term 1 on right hand side of equation 14 is approaching 0. That being the case, therefore V relative is 0. What does it tell us? What is when V relative is 0? That means the velocity of the particle and the velocity of the fluid is the same. So this implies that the particle trajectories are the fluid streamlines. So physically, when we try to think about this, what does this mean? If we have a particle with a very low Stokes number, they're going to follow the fluid streamlines. The fluid streamlines on which they are initially embedded. So, and what are the particles with a very low Reynolds number? So the Stokes number, a very low Stokes number. The Stokes number is dependent on d square. So it's proportional to the square of the diameter. So the smaller the particles are, Stokes number is going to get smaller even faster. So for those particles that are very small, typically smaller than 5 microns, because that's where the distinction is. Those are aerosols. They follow the fluid streamlines on which they are embedded when we are inhaling. Think about drug particles, think about particles with pathogens. They tend to follow the streamlines and go into our tape plants. While the bigger particles, they don't have this particular setup in these patterns. The V relative cannot be zero for the bigger particles with a stronger inertia. They cannot follow the streamlines. And as a result, they deposit much earlier. So whatever streamline they might be embedded in, they soon fall out of that streamline and deposit locally somewhere in the anterior part of the body. So the Stokes number hence helps us to understand where the particle might land in general. Does it make sense? Any question?
So here the relaxation time is 0.
Right, yeah. I mean, if you think about the Stokes number as another version of relaxation time, non-dimensional version of relaxation time, Stokes number will be 0 is relaxation time. So that's another way to think about it. Huh? Oh.
So it's almost 1 hour. You can in case any questions regarding this, then we can start the next session. So any more questions related to this, you can ask now.
Any other questions?
In the drop also, like remember if the drop is not exactly
Second?
if the drops are not typically water, like some polymer or something else, so the one thing changes is the density. So that brings the change in the Stokes also. So this goes to also.
Yeah, so basically then you don't only have to worry about the size, you have to worry about the rho p as well.
Yeah, means how then we can relate it to the actual drugs. They are not just
Yeah, so basically there is a problem that I have to solve. So when you are trying to evaluate the Stokes number, yes, the D is important. That's the mechanics part. The material part comes into the mu, not the mu, but the rho p. The mu is the mu of the surrounding fluid. So that is not the material property of the drug. The rho p is important. And if you have some kind of polymer, so that rho p is different. Now whether the rho p can balance the squared growth of the D is a good question, right? So if it is like say a point, even a 2 micron particle or 1 micron particle, because of that small d, there is always that huge impact on the Stokes number getting much smaller. Now whether the rho p not being 1000 kg per cubic meter but rather being 1100 kg per cubic meter, whether that is enough to balance that effect is a good question.
The consideration that you showed are the typical consideration that there won't be like much of a difference.
What do you mean by concentration?
Means
in your example that you showed before,
Oh, the compound concentration, yes,
milligrams or
yes. That's what
in those conditions it will be almost just like the
close to water.
like, very close. Not even more than 2%.
And that problem statement, if you read it, it said that this much in water. Now, if you start out with a different chemical altogether, can you still assume water like? It depends on the chemical, right?
If the base is different,
If the base is different, then
maybe if it's in alcohol, then maybe.
yeah. What's the timeline like?
So, like almost 1 hour. We started at 4:05.
Okay, so what we have here is, let me just quickly go through because I don't want to break at an odd time. So what we have next is actually a problem that we're going to solve. So yeah, so we are going to use these formulations, but it's a new problem, so we can stop there. I do plan to spend some time tonight to read the paper that I was telling you guys about, because I think based on my progress, you should be ready to at least read through the paper quickly tonight. Okay. Did you
You
share?
can send me, I will just, yeah, I will send it. At the end.
So it's on the cloud folder.
So
So
just tell me the name of the
I'll write it in the paper. There. Okay. So how long are we taking up?
So what is the time now? This is
Okay.
same time is 3:30. You can start at 3:30 and then if needed we can extend
Yeah.
like little more than 1 hour.
Right. Generation lung pathway with diameter 0.06 centimeters. So we are going to think about particle transport in these two very widely apart length skulls in terms of the spatial opening that it's moving through. Okay, so calculate the Stokes numbers. Calculate the Stokes number for a 1 micron diameter particle of specific gravity 1. So a water particulate. So calculate the Stokes number in the trachea, in the 16th lung generation, And part C, so based on the Stokes number, I would want you guys to comment on whether the inertial interaction is the dominant effect in the equation of motion or is it something else. So suggest whether inertial impaction could be an important consideration for this particle. Now, before we do any problem solving, just for the sake of the physiological realisticness of this problem, this 300 cc per second was very carefully chosen. It is equal to around 18 liters per minute, so which is pretty standard. So if you think about our breathing rate, if we are sitting relaxed, adults breathe at around 50 liters per minute. If we are walking around, moderate breathing is supposed to be around 30 liters per minute. If you are running, that rate goes up. So for any kind of study, right, we are trying to model breathing in different conditions, relaxed, moderate, heavy breathing. We go from a range of around 15 to around 55, 60 liters per minute. So that's why I chose that 300 cc number because that's not 18 liters per minute. Okay, so let's try to solve this problem. So let's first note down what we know about the particles. So here we have the rho p to be, the specific gravity is 1. So this is, the density of the particle is 1000 kg per cubic meter. The diameter is given us as 1 micron, so 10 to the power of minus 6 meter. The mu would be the mu for air, and that is 1.8 times 10 to the power of minus 5 kg per meter second. That is not given in the problem statement, but let's assume that we know it. The slip correction factor Cc is 1 plus 2.52. The mean free path distance divided by the particle diameter d. This is 1 plus 2.52. We have seen that lambda is 0.067 micrometer for air, divided by the diameter of the particle is 1 micron, right? Yeah. So, and we are basically trying to use this formulation. Stokes number is U naught rho p d square cc over 18 mu t. So this is, if you follow the equation numbers, is equation 13 on our lecture notes. Can you give me this number, the slip correction factor? 1.169 is exactly what I have. 1.169. Okay, so now what else do we need to use that formulation? We have the rho p, we have d, we have cc, we have mu. We have this capital D as well, right? Because those are the numbers that are given to us in terms of the generic diameters. What we don't have is the U naught. What is the characteristic speed of the flow through each of those regions? So let's get that. So for part A, which is when you are moving through the trachea. Trachea is, most of us we know what is trachea, so it's basically the bottom part of this pretty plate that we have, where everything is still going to one single tract. So trachea, the U naught in that region would be the entire flux divided by the cross-sectional area. So the flux is 300 cc per second. The cross-sectional area is it has a diameter of 1.8 centimeters, so pi 1.8 by 2 centimeters square. Can you give me this number? $117.9. So I have 117.85 centimeters per second. Since we are going to go to the MKS units, let's make it 1.18 meters per second. Okay, so therefore at the trachea, we have Stokes number as 1.18 meters per second. I'm basically just putting in the different terms in that red equation. The density is 1000 kg per cubic meter. That's diameter is 10 to the power of minus 6 meters square. The correction factor is 1.169 divided by 18. Mu is 1.8 times 10 to the power of minus 5 kg per meter second. And then the D, the characteristic dimension is the diameter 0.018 meter for trachea. So please give me this number. I have it as 2.3 times 10 to the power of minus 4. So hopefully I'm correct. So if you double check the number, it will still get 10 to the power of minus 2. No, minus 4. Minus 4 is correct. Okay. So this tells us that the Stokes number is very small. Even in the trachea. So what does that tell us about the initial impaction? The initial is not known. So that's fine. Now, this is at the trachea. We have to move to the 16th lung generation for the second part of the problem. What will change over here in terms of the numbers as we go to the lung, the tracheal, over the 16th generation of the lung? The flux will change. How will it change?
Probably it will get halved somehow.
It will get halved. Can you?
It will break into two and then.
So, if you think that the entire flux is going to be equally distributed throughout this bronchial pathways, we have to figure out how many bronchial channels are there in that generation. So how many bronchial channels are there in the 16th generation?
It breaks in a fractal, but
It breaks in a fractal way, that's nice, but can you mathematically quantify it? It's quite easy and very good. Very good. But then again, 23 is an approximate. It's coming from this variable. The funny thing is, the mathematics is so simple. This is 9th grade mathematics, right? And I recently wrote a paper. Thankfully, it is not published yet. It's still on archive. And I wrote the wrong generation number, and no one caught it yet. And it is in review at the results. I have gone through one there.
do we use this generation plus one there? But we have written 17.
I have written 16. No. Again, my bad handwriting. I mean, N.
So n generation is 2 to the power.
N generation is 2 to the power. Okay, so that's what we're going to use here. So I have this sketch in my lecture notes, but since I already drew it on the board, I'm not going to repeat it on this whiteboard. So the flux over here U is 300 centimeter cube divided by 2 to the power of 16 in this case, because that many number of channels are there to take in the airflow, times cross section for each. So pi times 0.06 is the diameter. So this is around 1.62 centimeters per second, or 0.0162 meters per second. So this is the min flux through each channel of the 16th generation. We can now plug this back in directly into the Stokes number formulation to get the Stokes number. So therefore, the Stokes number is 0.0162 meters per second times 1000 kg per cubic meter, 1.169 divided by 18, 1.8. Yeah. 1.8 times 10 to the power of minus 5 kg per meter second by 0.006 meter. So of course the rest of the terms are all the same as before. The only term that changed was this one, and it is much smaller than before. So in effect the Stokes number is going to be much smaller than even what we had before. So 9.75 times 10 to the power of minus 5, or of the order of 10 to the power of minus 4. So in both the cases, the Stokes number is much smaller than 1. The initial interaction is not going to be a big consideration in the mechanics of the particles in the system.
Gaia also is the Gaia of the electricity line.
Oh, right, that also changed, right? That's the So since, let me write down the statement for part C. Since in both cases, the Stokes number is much smaller than 1, therefore inertial impaction cannot be an important mechanism of local deposition. So what does this tell us qualitatively when you are trying to think about this kind of respiratory transport systems? What does it tell us if we are actually trying to target the bronchial region, the lungs? So at the lungs, the flux is going to be as small as what you see here. Going to your point, the balancing factor here was the diameter, right? The diameter of the particle sort of balanced that, or the diameter of the channel balanced that. So for what kind of particles would the initial motion be sort of relevant if you are trying to think about lung deposition? So this is the Stokes number. This D, which is the lung, the channel diameter, is going to be small. This 0.006. This flux is going to be small as well. So the only redeeming factor could be this particular term, 10 to the power of minus 6, which is what the small d was, the particle diameter, and it is helpful because it's a square term. So that means that if you have a larger particle, by a larger particle I mean something which is as big as 20, 30, 40 micron, then the initial impact could be relevant. And you might argue, does a 40 microparticle fit in those alveolar channels? Yes, it does. Because they are typically 100 microns. So if you are actually going into that kind of length scale for the particle size, then the Stokes number would be significant enough.
These micron size droplets no longer fragment into smaller droplets. Like let's say I start with 40 microns.
40 microns?
Is
What the droplet value?
No, no, I work in millimeter range. I don't think I will ever work with the micron range.
Even at 40 microns, see, the thing is, in our drug delivery modeling studies where we have to go till like a few hundred microns, like 100, 200 microns, we still don't think about fragmentation. But that being said, does it mean that it does not? I don't know.
Spray gun means answer this question.
But for infection transmission, I don't think that matters because there the particle sizes are already small enough. Because how does infection occur? Like, let's assume that I have some kind of infection and I'm letting out respiratory ejector which is infectious. The bigger particles, 50 micron onwards, are not going to go till pin. They're going to deposit. So unless someone's face is right next to your face, those particles are not important anyways. The particles that would be inhabiting are the smaller ones. So there, this effect is not important. Yes.
I remember there was a size classification which shows that as the size becomes smaller, it goes deeper into the respiratory tract. So there must be some cutoff size for the alveolar side. Then we can increase this. What was that? Around 50 microns.
It can
Otherwise it won't go inside. 0.5, that will definitely go inside.
Most of them will go, but some 2.5 micron particles, based on the particle trajectory, they can still deposit somewhere and nothing is stopping them from depositing it. But they will be better at focal instruments, of course. But 2.5 micron is still something, right? So there will still be some deviation from the particle. Okay, so let me write down one last statement here under this problem. So only the larger particles larger than a few microns, or typically what I was suggesting was something on the order of 10 microns, so 30-40 microns. So we'll experience significant inertial impaction in the lung region. But it can still happen because lung region still would allow those 10, 20, 30 micron particles to go through them because they're wide enough. Okay, so the next thing that we are going to do is dwell a bit more on what it implies by the particle relaxation time. And some of it we have already covered, but we have not yet put those things into words. So let's look at that, and after that, hopefully we'll have enough time for to quickly take a look at the paper that I want you guys to study tonight. Okay. So let's now go back to particle relaxation time. So let's move attention to tau, which was rho p d squared cc over 18 mu, right? Yeah, so this particular right hand side, as I said, if you just add a balancing cofactor that can make it dimensionless, then it becomes the Stokes number. So as a result, the Stokes number could be thought of as a dimensionless portion of the particle relaxation time. So let's write this down. So particle relaxation time so the Stokes number STK is rho p d squared cc over 18 mu u naught over d. So that if you take u naught down below, so 1 over d over u naught, that is that balancing time factor, can also be thought of as a dimensionless version of the particle relaxation time. Okay. For the sake of time, and these are all there in the lecture notes, can you redefine, and we have described this before lunch, so how can you define particle relaxation time in terms of the speed of the fluid flow and what the particle does in response? Anyone wants to take a shot?
When the relative velocity is zero.
Yes. So the time it takes to reach that relative velocity is here, right? So if you already have a fluid motion, if you drop, or basically if you embed a particle which is initially supposed to be having its own velocity to be zero, the time it takes for it to attain the fluid velocity so that V well becomes zero. And the other way around, if the particle is moving, the time it takes for it to slow down and become or achieve the fluid velocity. So let's not write all those details down. Let's directly go into further developing the equations that we have. So we have STK is dV prime dt is equal to minus V rel. Where is this coming from? This is coming from equation 14. So equation 14 was this. So STK dV prime dt prime is equal to V setting over A naught. Now we are ignoring the gravitational term. We are just including the V relative term into the mathematics over here. So if this is the case, let's now think about the non-dimensional terms that we have used. So dV prime is again V over U naught, and V relative is V minus V fluid over U naught. And we have written these definitions down already before. Now let's try to solve this particular equation and see what we get. So dV prime over V relative is equal to minus 1 over STK over dt prime. There was a t prime over here. Sorry. T prime here. So we have just changed sides. Let's now try to integrate this and see what we get. So we are integrating the left hand side and the right hand side. So this becomes, but no, can we still integrate it? No, we cannot, because that is still the v prime step on the left hand side. So we have to think about converting it to the v relative. Let's do that first. So before we manage to integrate this, the v relative is v prime minus v of the fluid. Now what is v prime of the fluid? It is u naught. So we are thinking of a situation where the velocity of the fluid is constant, and we are non-dimensionalizing it with respect to its magnitude. So this by itself is a constant term, the non-dimensionalizing version of the v fluid. So if we take that into account, and if you think about taking the derivative of this particular equation, dv bar prime is equal to dv relative prime. So now instead of writing it in the dp dot prime form, we can add this subscript that this is also equal to the relative. Yes.
When we started with u naught as a characteristic, we are scaling for the velocity.
Right.
So u naught bar by u naught is just one unity. Right? U naught bar is not different from u naught.
But we are assuming now that the velocity of the fluid is constant, which is u naught. U naught initially was the characteristic velocity that we are using to non-dimensionalize the different velocity lines. But over here in this particular set, the fluid itself has a constant velocity, which is that. Right? So if that is the case, then that becomes, in effect, that becomes a unit length. And it becomes a constant term which you take the time derivative of this. Does it make sense? Or in other words, if you think about going back to the same definition of the particle length in time, something is moving at a constant speed. You embed a particle, the time it takes to get to that speed. Right? That speed is constant. Or if you have a static medium, you throw a particle, it has its initial speed and then it gradually slows down. But that initial thing is still exists. It is zero, that constant value. So this being the case, this is constant, so we can time derivative and then that equation is equivalent to taking the d of relative prime. Does it make sense? Okay. So this is what I get by skipping a few steps. So I should not get into that. Okay, so this is what we have. Let's now randomly put the integral signs on the two sides. So now we have on the left hand side natural logarithm of v relative is equal to, this is just minus t prime by stk plus some constant of integration a. Now we have to figure that out, what is that constant of integration, but before that let's do the exponentiation over here. So exponentiating, we have v relative prime is equal to e to the power of minus t prime over stk minus a. Okay? Now let's try to figure out this constant. So at t is equal to 0, we have v relative prime at t is equal to 0 is v bar prime minus v bar of the fluid at t is equal to 0. Now what is v bar prime at t is equal to 0? If you think about the first scenario, you are embedding a particle in a fluid that is moving. 0. So the particle is at rest and then it's gradually will return the fluid velocity. But it is 0 initially. So this is 0. The fluid is moving at u naught. So what is that particular term? It is a non-dimensionalized version, so it is what we just wrote a while back, this. Now also we have t prime, which is the non-dimensional time that we are using in this equation, that is equal to the actual time divided by d over u naught. So at t is equal to 0, this t prime is also equal to 0 because it's this, which is trivial. Now let's come back to this particular form again that we have derived. Let's apply this over here. So therefore, enforcing the initial conditions on this particular equation, you can still see the equation? Yes. So on this equation, I'm enforcing the initial conditions. We have minus u naught over u is equal to e to the power of a. How we are getting to that? This becomes, so this t prime becomes 0, so that becomes 0, and the v value becomes minus u naught over e naught. So just putting those things in, this is what we have. Okay. So actually we are going to use this in the subsequent steps. So let's call this equation, I don't know what equation numbers we are in, so let's call it 17 for now. But again, for the equation numbers, follow my lecture notes because those things can get confusing eventually. So now in the previous equation, we had v relative prime is equal to e to the power of minus t prime over stk plus a. So we are now going to break this right hand side into e to the power of a times e to the power of minus t prime over stk. We have already figured out what is this e to the power of a. So this is, as I said, we are trying to figure out the constant of integration. We now know that that constant of integration related term is coming from equation 17. So let's plug that in. Sorry, I missed this 0 over here. So let's plug that in. V bar prime relative is minus u bar divided by u times e to the power of minus t prime over stk. Okay, so what do we have here? This is the unit vector, right, of the fluid flow. This is the velocity of the fluid in this case, and this is the magnitude, so that is the unit vector. This is the relative velocity of the particle, 0 prime, in the non-uniform form, and there is a negative sign. So can we write this from here, that the magnitude of v relative is e to the power of minus t prime over stk? Yes, we can, because this is the unit vector, as I said. So once we have it in this form, this gives us a very clear idea about how the relative velocity of the particle would evolve over time, be it a growth or be it a decay. It is a growth when you have a moving fluid and you are emitting a particle out. Let's call it equation 18. So from equation 18, it follows that a particle moving in a uniform flow and initially having a velocity different from the fluid around it will have its velocity decay exponentially until it attains the fluid velocity. the same speed as the ambient fluid. Okay, so that being the case, let's now look back again at equation 18. What if we assume certain numbers for that t prime? What if we assume that t prime is the Stokes number? Or in other words, the Stokes number was what? The dimensionless version of the particle relaxation time. What if we assume that to be the t prime? The dimensionless particle relaxation time, what happens then? So, again from equation 18, if this t prime is stk, therefore the v relative would be e to the power of minus t prime over stk, or e to the power of minus 1, right? So how much is that? Can you quickly use your calculator to tell me how much is that? E to the power of minus 1? 0.367. So let's just call it 0.37. Or this is V. What is V rel prime? V rel prime is, based on the definitions from morning, without any kind of consideration about the uniform flow, etc., etc. V rel was, at the very basic, V rel divided by the characteristic speed, u0, and that is equal to this 37%, right? Or this V rel is now 37% of this fluid that is moving at u0. So, what does this tell us? This tells us that Stokes number is that non-dimensional time that is needed for the particle to achieve 37% of the mean speed of the ambient flow. So, the Stokes number can be thought of as the non-dimensional time needed for the particle's velocity relative to the fluid to change to 37% of the main flux value, right? And if you think about the decay, of course, the plot would look like this. So if you look at any paper that are studying these kind of systems, if you think about the V rel based on if it's a decay, this is what it looks like. Questions on this? I think we still have enough time to complete this and get to where I wanted to go to. So from this consideration again comes the concept of particle stopping or starting time. So let's quickly derive that, and since we already have the velocity formalisms, it is now integrating to the spatial coordinates. So now comes the particle stopping or starting distance. Okay, so we are going to use the same formalism for the V rel, but now we have to add this extra term that dx dt, and this is still the relative, is equal to this v relative, and we are still in the non-dimensional world, so those primes are still there. So dx well prime over dt prime is equal to v relative prime, and this v relative prime, as we have seen, is minus u naught over u naught times e to the power of minus t prime over stk. So this x prime x bar prime relative is the dimensionless spatial coordinates of the particle. Okay, so let's try to integrate this with respect to time. So integrating with respect to time, we get x relative prime is equal to Stokes number. The negative sign gets cancelled, so we get a positive cofactor u bar over u e to the power of minus t prime over stk plus a constant. Okay, so assume that it is 0 at t is equal to 0. So what does this imply? So what is x this particular term that I have defined? So x bar real non-dimensionalized is the particle's dimensionless position relative to a fluid particle, right? So initially, when we are embedding the particle into the flow, we are comparing with respect to the fluid particles that is at that particular location. So it's not the absolute location of the particle; it's with respect to the fluid. And the way we are thinking about the problem physically, that implies that as an initial condition at t is equal to 0, we can reasonably assume that x relative bar prime is 0. So that being the case, yes. This stk will be 1 upon stk. Okay, right. So you mean this term, right? Yeah. No, electron. No, this is right here. This was not a differentiation, right? This was an integration. You are trying to change a whole subset of the and that is scary after 200 years of doing that. Yeah, the Evangelista just told me during lunch, like, Navier-Stokes has been around for 200 years. So someone that we both know told us why we are still doing fluid mechanics. Okay, so this is the initial condition. So therefore, we have this constant is equal to, what are we left with in the constant term? So if t is 0, we saw in the previous case that t prime is 0 as well, so this becomes 1. We are just left with this cofactor, Stokes number times u bar over u. So this constant becomes negative Stokes number because this goes to the other side times u bar naught over u bar. Sorry, u. So let's put this back into the equation. Therefore, x relative bar prime is equal to minus u bar over u naught, Stokes number, 1 minus e to the power of minus t prime over stk. Now this is a unit vector again. So if you think about the magnitude of this of this dimensionless position for the particle in the fluid, we have x relative is Stokes number times 1 minus e to the power of minus t prime over stk. So what do we have? So we started out from the concept of denoting the concept of stopping of static distance. So where do we stand in terms of that? So if you think about stretching the time to infinity, so you can write the definition of the stopping and starting distance like this. So let me write down the definition. So stopping or starting distance is the separation at when we stretch the time to infinity, separation at t is equal to infinity between the particle and the fluid element it was embedded in at t is equal to 0. Right? And that was quite evident in the way we took the initial assumption that the x relative was 0. So that the fluid element on which the particle is getting embedded is intrinsic towards our understanding of this problem.
Earlier we mentioned it in the Stokes definition also that we have CC down, which captures the effect of lambda.
Yeah.
So that means that that is still valid for this also.
Yes.
So now when we say the unitary part is important, when we say the particle velocity with respect to the fluid, we are talking about with respect to the molecules of fluid.
Okay, that's a good question because the mean free path is a material problem, right? When we are talking about the fluid element in this case, we are over t, right? If the t becomes bigger, anywhere CC becomes close to 1. So even if you do keep on including that in the mathematics, it doesn't make any difference to the work. Okay, so this big, any other question? Okay. T approaching infinity, the x bar, we are going to call it stop because let's assume that it's a stopping distance. This t bar is t prime is approaching infinity, t is approaching infinity. But d is the characteristic dimension of the flow is equal to the Stokes number. So here d is the characteristic dimension in the flow. So the Stokes number in this case is the ratio of that stopping distance over the characteristic dimension in the channel, whichever region of the airway being the example we discussed and you are trying to study. Any question? So all these things help us. These are not, until now, whatever we have done, it does not capture the complexity of the geometry that I have shown you in the morning, right? It is trying to capture the complexity of, or rather trying to look at how you can use the governing equation of motion towards understanding the generic trend of the particle transport. If the Stokes number is low, the particles are going to follow the stream length, they will penetrate further into the air. If the Stokes number is high, it's not going to. There will be inertial impact and the particles are going to land much earlier in the area. So this just gives us a qualitative way of understanding the particle transport trends. Now, I think I have vanished within the correct timeline. So the paper that I want you guys to study, I have put it on the shared folder. It's this paper by someone, Sunny Jam. So he is a faculty in biological and environmental engineering at Cornell. So he wrote this paper last year. So I'm not going to tell you why I want you to study this paper. Just go through it tonight, and we will know tomorrow why I asked you to study this. Similarly, I think tomorrow night and day after tomorrow there will be a couple of more papers that I want you guys to go through. But this is your first chance. The lecture notes are there on the top folder.
Yeah, I will say that.
I think on the lecture notes you can note down we have covered till the first 20 pages today.
So is this like enough or it can be extended by half an hour, 45 minutes?
No, the one is I would like to stop now because now
No, this is fine. I'm just asking there because like I have kept like 4 hours each day. Maybe like there can be half an hour or 45 minutes extra.
How long did we
Some
do
days.
today?
Huh?
How long did we do today?
It was effectively 3.5 hours because the first session was not that much. From next day onwards we can like use complete 4 hours.
Yeah.
And if needed maybe like 35 minutes extra someday.
And yeah, so tomorrow part of it will still be analytical derivation. And I want to introduce the details of the respiratory geometry to you guys as well. Now, question for you: how many of you have